Okay, so today we're just going to discuss a few midterm things and then go over a couple of homework problems that it seems like most people are having trouble with. All right, so the first thing about the midterm is how to study for it. So the most important thing to do is just do a lot of problems. I know a lot of people kind of spend the bulk of their time studying, like just reading the textbook and looking at other solved problems, but that really eventually will stop working at some point with physics. And you kind of just have to switch to just doing problems over and over and over again. So make sure you do a lot of problems, do all the lecture problems, do them over and over and over until you understand what we're doing. Same thing with the homework problems, with the discussion problems. Just do them as many times as you have to do, and eventually it will start to click. Unfortunately, reading the textbook I find is not as efficient and not as useful as just doing problems, because when you sit down and do a problem, you can tell if you know how to do it or not. When you're reading a textbook, it's very easy to think you understand something, and then when you actually have to do a problem involving it, you realize you don't know what to do. Okay, that's the first thing. Do a lot of problems. The difficulty of the midterm will be very similar to the homework, very similar to lecture problems, very similar to discussion problems. So anything we didn't cover in any of those, any topic that was not covered in discussion, lecture, homework, will not be covered on the midterm. So if there's some sections of the book that we skipped over, if I didn't mention them in lecture, for instance, we didn't talk about temperature dependence of resistivity, that's not going to be in the midterm. You don't need to know anything about that. So only things that we actually covered in lecture and discussion and homework will be on the midterm. And the other thing is about the multiple choice. So I know obviously that it's not ideal to have a multiple choice. I would like to give you an exam where you can show your work. That way if you make a silly mistake, you don't lose all of the credit for adding 2 plus 2 wrong. However, with the online, everything being online, it's extremely tedious and time-consuming for the TAs to grade online work, especially in a big class like this. And grading is already tedious and time-consuming, so online makes it worse. It ends up taking way too long to grade, and it just really wouldn't be efficient for a summer course, especially. So we're going to make a multiple choice. I'm going to do my best to make it fair and balanced so that you have plenty of problems to do, so that if you make a silly mistake on one of them, it doesn't drop your grade by 20 points, but also, not give you like 50 problems to do in an hour, obviously. So I'm going to try to balance it so that it will be as fair as possible. And then also the last thing is the formula sheet. So I'm a little bit hesitant to give out a formula sheet because I find that it, again, kind of tricks people into thinking that they can get by just with the formula sheet. I see students, they don't really know what the formula is for. They'll just write down a random formula and apply it in the wrong situation, which, I understand. I was a student too, like we've all done it. So I actually find that people do worse when I give them a formula sheet. So make sure that you actually use the formula sheet to your advantage. Make sure you study the formulas on the formula sheet so you know when they're applicable, what all the variables in each formula means, so that you don't kind of fall into this trap of like, oh, I have a formula sheet, therefore I don't need to study the equations. That usually ends up backfiring. So make sure you actually study the formula sheet, know what all the formulas are for, know what every letter stands for, and when you can use each formula. So the biggest thing to make sure that you know how to use is Gauss's law. Okay, Gauss's law is like the most important thing we've done. If you don't study anything else, make sure you study Gauss's law. So for Gauss's law, remember you can only use it when there's spherical symmetry, cylindrical symmetry, or plane symmetry. So study those cases. Make sure you know how to use Gauss's law to find the electric field in a sphere or some kind of spherical distribution. Make sure you know how to use it for a cylinder, and make sure you know how to use it for an infinite plane. Also, I would just memorize the results of that. So for a sphere or any kind of spherical distribution, make sure you know it's just q over 4 pi r squared, and that only applies to a sphere or a point charge. For cylindrical, just memorize the electric field of an infinite cylinder, an infinite line, and then for the infinite plane, again, make sure that you just memorize the electric field of an infinite plane and how to use Gauss's law to arrive at those answers. Those are like the most important things because we use these over and over and over again. Okay, another thing that people make a lot of mistakes on is getting confused between a general formula and a formula that's specific to a point charge. So our electric field, we have Q over 4 pi epsilon naught r squared. When we have Coulomb's law, we have Q1, Q2. These are only for point charges, okay? So a lot of people will, anytime you have, distributions, charge distributions of any size, any shape, they jump right here and use this. But this is only true for a point charge or outside a sphere, because a sphere looks like a point charge outside its radius. So make sure you know that those are only for point charges. The same thing goes for the potential. The potential of a point charge only is given by this, okay? So this is only for a point charge or outside a sphere. The same thing goes for potential energy. Again, this is only for 2 point charges or 2 spheres. And then another common form of the potential is when we're inside a capacitor. So when we're inside a capacitor, remember, the potential is given by the electric field in between the plates times the distance between the plates, the plate separation. So again, this potential is only valid in a constant electric field when we're looking at a capacitor. So do not use this for a capacitor. Do not use this one for a point charge. So make sure you know for what setup each potential applies to. So that's really the most common thing I see people making mistakes on, is just basically confusing equations that are for point charges and equations that are not for point charges. So make sure that you know those differences first and foremost. That's probably the most common mistake I see by far. Okay, so let's go over one of these homework problems. So this homework problem was from homework 3. So, whoops, in homework 3, this was variational problem 22.10. So we have a sphere of radius 5 centimeters. So the radius is 0.05 meters. And it carries a charge of 3 nanocoulombs. So it has some radius and it has some charge on it. Calculate the electric field magnitude at a distance 4 centimeters from the center of the sphere and a distance 6 centimeters from the center of the sphere. If it is a solid insulator, and then if it's a solid conductor. So for part A, if it's a solid insulator, that means that the charge is spread uniformly throughout. So our charge is going to be spread out like this. Okay, and first we want to find the electric field inside the sphere. So what we're going to have to do is use Gauss's law. So we're going to do E dot D So the Q enclosed is the tricky part here, because if we have a uniform charge distribution, we can't just write Q. We have to find the charge enclosed will be the charge density times the volume of the Gaussian, the volume enclosed by the Gaussian surface. So we're going to pick just like some, we're going to have some Gaussian surface in here. This will be, let's say that's 4 centimeters where we're looking. So to find Q enclosed, let's find rho first. So rho is just going to be the total charge divided by the total volume. So this will be 3 nanocoulombs divided by 4/3 pi r cubed, where r is the total radius of the sphere. So this will be 3 times 10 to the negative 9 over 4/3 pi. The total radius is 0.05 cubed. And that comes out to 5732 times 10 to the negative 9 coulombs per meter cubed. Okay, so this is a charge density. Now we can find the Q enclosed. So the Q enclosed at 4 centimeters, so we're looking at 4 centimeters, is just going to be the charge density times the volume at 4 centimeters. And then we divide by epsilon naught. So we're going to have rho times 4/3 pi little r cubed over epsilon naught. And then over here, so our Gaussian surface will be the surface area of a sphere at 4 centimeters, so that will be 4 pi r squared. So let's just see, we can cancel some things here. Our 4 pi's cancel. r squared cancels with r, and we end up with E is equal to rho times r over 3 epsilon. Now this is a very common result when we have a uniformly charged sphere. Our electric field inside the sphere will always be given by this. So now all we have to do is just plug in our numbers, so 5, 7, 3, 2 times 10 to the negative 9 for the rho, and then r is 4 centimeters, so it's 0.04, and then divide by 3 times epsilon naught, and that comes out to 8,630 newtons per coulomb. So that's the answer for part A. So again, this is just the electric field inside a uniformly charged sphere. And then for part B, we have, it's just going to look like a point charge, right? Because now we're outside the sphere, so it's just going to look like a point charge. So we're just going to have Q over 4 pi epsilon naught r squared. So Q we know is 3 nanocoulombs, 4 pi epsilon naught, and then r is 6 centimeters, so it's 0.06 squared. So this comes out to 7,490 newtons per coulomb. Okay, and now you notice that the electric field outside, 1 centimeter outside the radius, is actually less than the electric field 1 centimeter inside the radius. And this makes sense because if we were to plot the electric field, so the electric field versus R, now we found that inside, so when we're inside the sphere, the electric field has a R dependence, so it's directly proportional to R, so it's just going to look like a straight line, okay? And then outside, it has 1 over r squared, so it looks like a point charge, and it's going to look like this. So this is proportional to r, this is proportional to 1 over r squared. So it makes sense that, 1 centimeter outside the sphere is less than, 1 centimeter inside the sphere. So this is if it's a insulating solid sphere with the charge spread evenly throughout. Now, if it was a solid conductor, how would this change? Well, if it was a solid conductor, we know right away that this part, whoops, this was not actually part B. So if it was just a solid conductor, this part would not change. So if it was a solid conductor, we know that all of the charge would be on the outside, right? And it would be uniform. And we know that the electric field inside a conductor, so at R is equal to 4 centimeters, we know that the electric field inside a conductor is 0. So that would just be 0. Now, when we're outside, so at R is equal to 6 centimeters, it's going to look exactly the same, right? Because the electric field is still going to be the total charge divided by 4 pi epsilon naught r squared, because outside the conductor it just looks like a point charge with the total charge Q on it. So this part will be the same from our previous problem. So this, we said, was just equal to 7,490 newtons per coulomb. So this is the same as in our previous part, and then inside the sphere now it's 0 because it's a conductor. Now let's just, I just want to draw a plot of this. So when we had the solid, the insulator, so we had the uniform insulator, our electric field looked like this, right, where this was proportional to R, and this was proportional to 1 over r squared. But when we had a conductor, it's going to look like this, where it's 0, and then at R, it just jumps up and then goes off. So This is also important because anytime you have a conductor, the electric field will have a discontinuity at that surface. So our electric fields will generally always be continuous, like here. We had a continuous electric field, even though it had this little spike, it's still continuous. But when we have the surface of a conductor, the electric field will have a discontinuity there, always. So always at the surface of the conductor, there will be a discontinuity in your electric field, so it's okay to have your electric field kind of jump up like this and then go back down. Alright, so that's the difference between an insulator and conductor. Alright, so let's do this problem from homework 4. So this is homework 4, variational problem 23.1. So here we have an electron. It's at rest, so we have this lead atom 10 to the negative 10 meters away from our electron. So this is 10 to the negative 10 meters. Okay, we're given the charges. We can treat each as point charges. How much work would you have to do to move the electron to a distance 5 times 10 to the negative 10 meters from the center of the lead nucleus? So we're moving the electron from here to a distance further away over here. So we'll call this like point B. So this is point A. And this now is 5 times 10 to the negative 10 meters. Okay, and then the lead nucleus has a plus charge of 82 electron charge because it's got 82 protons in it. All right, so how much work would you have to do to move the electron? So the first thing is to notice that it says you. So how much work would you have to do? So that's the most important word here because it's not asking you how much work would the electric field have to do. It's asking you how much work would an external force you have to do. So remember, the work done by the electric field, right, will be equal to negative change in potential energy, right? So that's the work done by the electric field. But now an external force, so we'll call that electric field, an external force will do the negative of the work done by the electric field, right? Because whatever work I do, the electric field has to do the negative of that and vice versa. So that means that an external force does the positive change in potential energy, which is UF minus UI. So I've had a lot of questions about that. So anytime it says how much work would have to be done to move something, it's always meaning an external force. If they mean the electric force, they'll say, how much work does the electric force have to do? But typically, we usually end up talking about an external force. So another way to think about this, so we know that this work that we have to do is going to be positive. And I know that because I have a negative charge and a positive charge, right? So if I have a negative charge and a positive charge, they want to attract each other. They want to be closer together, and they're going to have less potential energy when they're close together because that's where they want to be. So if I try to move this electron further away, it's getting attracted to the positive charge, right? So I'm going to have to really pull it and put work in to move it away, right? Because I'm working against the electric force between them because the electric force wants to pull them together. I'm trying to now pull them apart. So I'm going to have to add work to that system because I'm increasing its potential energy. So I'm going to have to put positive work in there because I know its final potential energy is going to be higher than its initial potential energy since I'm pulling them apart and they want to attract. Okay, so remember that the potential energy for point particles only is given by Q1, Q2, 4 pi epsilon naught R. And this is another thing to keep in mind. A lot of times students will write R squared at the bottom of potential energy because that's similar to Coulomb's law and it looks very similar. But potential energy only has one R in the bottom, so be very careful of that. All right, so the U final is the charge of the electron times the charge of the lead over 4 pi epsilon naught. The final distance between the two is 5 times 10 to the negative 10. And then subtract that from the initial, which is 10 times 10 to the 10 to the negative 10. And then for the electron charge, just plug in the actual charge of the electron. And then for the lead, 82 times, the charge of the electron, which they give you here. Remember, one's negative, one's positive. Okay, and then we do that, and we end up with 1.51 times 10 to the negative 16 joules. So, as we expected, that comes out positive. Okay, so that's the first part. Now for part B, so this was all part A. For part B, if you release the electron from the position in part A, so if you release it from where it is right here in part A, what will be its kinetic energy when it's a distance of 8 times 10 to the negative 12 meters from the center of the lead nucleus? So that means like when it's really close right here, what will be its kinetic energy? So we're going to use conservation of energy here. So we're going to have E initial is equal to E final. Now I only have kinetic and potential energy. So the kinetic energy of the electron plus its potential energy plus, no, oops, that's going to be final potential. Okay, so initially it's at rest, so that means that this is 0, right? Its initial kinetic energy is 0 since it starts at rest from this point. Then its initial potential energy is the potential energy just between the lead and the electron, which we found before. And then the kinetic energy, the final kinetic energy is what we're looking for. And then the final potential energy now is at this distance 8 times 10 to the negative 12. So we just plug in 8 times 10 to the negative 12 there. Solve for Ke, so just plug those numbers into your calculator and find what the final kinetic energy is. So you will get 2.7 times 10 to the negative 15 joules. Okay, so that's its final kinetic energy. So that's what we would expect if we release it from rest. It's going to be attracted to that lead nucleus and move towards the center of the lead nucleus. So one thing to keep in mind with this, again, like I said, the most important thing and the thing I've been getting the most questions about is this right here. So just, I know it's hard to keep track of all these negative signs, but think about it intuitively first. You would expect in this problem to have to put in positive work to separate two charges that want to attract each other, right? You'd have to add energy to get them to separate because they want to be together. So then the other thing to remember that I've also gotten a lot of questions about is remember that kinetic energy is a scalar, right? So kinetic energy is a scalar because this velocity here is just, it's speed, it's the magnitude of the velocity. So kinetic energy is a scalar. If you have multiple particles, now the reason that I only included the electron's kinetic energy here is that they told us that the lead atom or the lead nucleus was at rest. So the lead nucleus has 0 kinetic energy both in the beginning and after. But if the lead nucleus was moving, then you'd have to include also the lead nucleus kinetic energy. So remember, kinetic energy, if you have more than one particle that are moving, then you have to take into account both of those particles' kinetic energy. So here, only the electron was moving, so I just had one kinetic energy to worry about. So kinetic energy is scalar. You have to think about the contributions from every particle that's moving. And it's also always positive. So remember, kinetic energy is also always positive. Because if you look here, the mass obviously is never negative. We never have a negative mass. And since this Vf is really the speed, it's a magnitude. We know magnitudes are never negative. Speed is never negative. So kinetic energy can never be negative. A change in kinetic energy obviously can be negative. But a single value of kinetic energy is always positive. And then the same goes for potential energy is a scalar. However, potential energy can be positive or negative. Right, because if we have, if one of our charges are negative, then our potential energy between the two will be negative. So, okay, so that's what to think about there. Now, this next problem we're going to do is from homework 5. This is probably the problem I got the most questions about, and it is probably one of the more challenging ones for sure. So this one's from homework 5. It's PSS 23.1. Okay, so for this problem, we have a insulating sphere with uniform charge density given by rho is equal to 6.6 times 10 to the negative 7 coulombs per meter cubed. We're told the radius of the sphere is 0.4 meters, and we want to find the electric potential at a point 0.2 meters, so that's inside the sphere. So we're looking at some point here. This is our radius. Okay, so we're looking at some point in there, so what is the potential there? So again, this one's challenging. So what we have to do is integrate over the electric field. So we have to use this for the potential. Okay, so we have to do it this way, and we'll see why in a second. So the first things that we have to do is find the electric field everywhere. So the electric field, as we saw in the first problem we did, we're going to have one electric field outside the sphere, and then since this is an insulating, uniformly charged sphere, we're going to have another electric field inside. So E in, again, as we found in the previous problem, so I won't go through this again, but you can do Gauss's law exactly the way we did in the first problem and find that the electric field inside is rho times r over 3 epsilon naught. And then outside, we know that it's going to look like a point charge. Okay? So that's the electric field inside and outside. Now, one reason why we have to, or the reason why we have to integrate over the electric field is that inside here, so when we're inside the sphere, and it has all these point charges everywhere, uniform, so they're everywhere here. We can't just say, oh, the potential, is inside is Q over 4 pi epsilon naught r, where r is, that 0.2 meters in. You can't do that because the potential, if I drew my Gaussian surface like somewhere here, the potential inside some region depends on the charge outside. So remember, this was not true for the electric field, so that's how we can use Gauss's law to find the electric field in cases like this, is that for the electric field, this charge out here, outside our Gaussian surface, does not contribute to the electric field, right? So only the charge inside contributes to the electric field from the charge inside. But that's not true for the potential. So if you're trying to find the potential due to this charge in here, the charge outside actually affects the potential. So that's why we have to integrate. We have to start from 0. We know the potential is 0 at infinity. We have to integrate all the way in. So again, now why the potential is affected by charges outside your Gaussian surface, you don't need to worry about. Again, this is like the most complicated type of problem we're going to do for potential. So, just trust me that the potential is affected by the charge. We have to integrate. Okay, so now let's start our integration. So this electric field, so we want to integrate from infinity, where our potential is 0, to some point inside the sphere R. There are two different electric fields we have to integrate, right? We have to integrate over this one and over this one. So what we're going to do is actually break this up into two integrals, since we have two different functions we have to integrate. One is valid from infinity to the surface of the sphere, so from infinity to R, which is E out, and we're integrating in the R direction. And the other one is valid from the radius of the sphere into that point we're looking at inside the sphere, so from capital R to little r, and that's E in. And again, we have to just break this up because there are two different electric fields in two different regions. Okay, so all we have to do is then just plug this in. So from infinity to R, we have Q over 4 pi epsilon naught r squared dr. And then from R to little r, we have rho r 3 epsilon naught dr. Okay, so let's integrate this. So we get Q over 4 pi epsilon naught R, which is the potential for a point charge. So that looks good so far. Because outside the sphere, we would expect it to look like that of a point charge. And then this second term here inside, when we integrate, we're going to have rho 3 epsilon naught, and then we're going to have a 1/2 r squared from capital R to R. And I'll again prime this to distinguish the r's. So we're going to have rho over 6 epsilon naught r squared minus capital R squared. Okay, and then that's going to be your potential. So again, I know obviously the numbers in mass and physics are different, so just plug in whatever numbers you have into this, whatever Q you're given. You will have to find, actually you'll have to find the total charge, right, by multiplying rho times the volume. So you'll have to find the total charge, plug that in here. Your capital R is the radius of the sphere. Your rho was given to you, and then this little r is the radius or the distance that you're looking for the potential. So in my case, it was 0.2 meters. So this is your point inside the sphere, and then just plug that in, and that's your answer. So with the numbers that I have here, I got 5465 volts. Okay, and then just one more thing I want to go over quickly is about capacitors and batteries. So if I have a capacitor, and let's say I have positive sigma and negative sigma on the other plate, and I connect a battery to it. So my battery is here. So we did some of these problems, I think, in chapter 24, and we had the dielectrics. So what's the difference between, you'll see problems that say you disconnect the battery or you keep the battery connected when you insert a dielectric. So if I insert a dielectric here, so I put some dielectric with dielectric constant K, if I remove the battery, and I have some potential difference V across the two plates, right? So if I remove the battery, the charge on these two plates has to stay the same, right? Because if there's no battery here, there's nothing that can like pump charge to the plates. So the the charge on the plates has to stay the same. So plus minus sigma on plates is constant. And that means that when you insert your dielectric, the induced charges on the dielectric is going to decrease the electric field, right? It's going to decrease the potential by an amount K, which is dielectric constant. So this is what it means when it says you remove the battery. Basically, it means that the potential between the plates does not have to stay the same, and in fact, it will not stay the same because there's no battery there keeping it the same anymore, right? So only the charge on the two plates will stay the same because once you put the charge on the plates from the battery and now you disconnect the battery, there's nothing there to put more charge on the plates. So the charge on the plate stays the same, the electric field and the potential between the plates does not stay the same. Now what if I say I keep my battery connected and I insert a dielectric? So now I keep my battery on, so it's still supplying a potential difference of V between my plates, and now I insert a dielectric. So now the amount of charge on the plates can increase, right? Because if there's a battery supplying a potential difference between the plates, when I insert my dielectric, the potential difference will not change anymore because the battery is keeping it constant at V. So V will stay the same. And the amount of charge on the plates will actually increase. Because the battery wants to keep the potential difference between the plates the same, so it's going to pump as much charge as it needs to get that potential difference between the plates equal to V once you insert the dielectric. So that's the difference when you hear a problem say you keep the battery or you disconnect the battery. That's what they're saying. Basically, does the potential between the plates stay the same or not? Does the charge between the plates stay the same or not? Okay, and then just one other thing also with circuits. So if I have a circuit, and let's say I place a battery here, and another battery facing the same direction here. So this is my positive plate on each. And let's say this battery is like 10 volts, and this one's 5 volts. So this battery with the 10 volts, so any battery is going to want to pump current from its positive terminal. So any battery is going to want to pump current in that direction. But this battery down here also wants to pump current in this direction. So you can't have current going in two different directions, right? So the way you do this is you look at it and say, well, which battery has a higher potential? And the one with the higher potential will win out. So in this case, the charge will actually flow clockwise because this battery has a higher potential, so it will be more able to pump charge, basically, around this circuit. Now, if, let's say it was opposite, where I had, if this was the positive terminal here, now both batteries would be pumping the charge in the same direction, and we'll just go around in the clockwise direction. Okay, so that's really all the topics I wanted to cover today. Again, the midterm will focus mostly on chapters 21 through 24, since I know you didn't really have a lot of time to absorb circuits. So, maybe one or two questions on circuits and stuff. The majority of the midterm will be on things like this that we just did, calculating the potential, calculating the work done, finding the force between things, stuff like that. Okay, so that's it for today.